Good morning and welcome back. It's me again. Using the upload the video to YouTube, um, it's it's good and also not good. It's good because we can you can learn and anytime, anywhere. Okay, that's good news. And I don't have to reiterate the course material. If you don't understand my points, uh, you can study course material again and again and again. But the disadvantage is I do not have a chance to see your response in face. See your response is quite important because that is interactive. I can interact with you, answer your question immediately. Okay, so you are welcome to my office. During my office hour, everybody is welcome. You don't have to make a reservation. Just come. Okay, let's start today's course. Today we will talk about section 3, covariance of electrodynamics. That means all the uh, electrodynamics, all the equations are invariant in form. Invariant in form in all the Lorentz frame, all the inertial frames. They should be the same. That's interesting. I will show you. Today we will cover only 7 pages, not too much. Our progress about this course is quite good, so I don't want to speed up. We can slow down and give you a lot of time to digest, to understand the material, the course material. Okay, so first, let me show you. Last time we talked about relativistic mechanics. Newton's law has been radically modified for the special theory of relativity. The electromagnetic laws, divergence theorem, Coulomb's law, Faraday's law, Ampere's law, do not need any modifications because they are already covariant. However, the covariance of these laws, Maxwell equations, is not immediately clear from the equations by which they are usually represented. So it's not very clear. For example, divergence B equals 0. It's not clear from this viewpoint that different observer will have the same equations, will see the same equations. So we have to do something. So our purpose is to prove that the EM laws are indeed covariant by casting them into relations between 4 tensors of the second rank. So we will have the 4 tensor of the first rank, 4 tensor of the second rank, and 4 tensor of the third rank. They will transform according to the Lorentz transformation matrix. Okay, we will do this by first define 4 tensors in terms of a known EM quantities, such as potential, scalar potential, vector potential, current, charge, EM fields. And we will form the equations with 4 tensors of the third same rank. Then, show that one or more existing EM laws are implicit in each equations. Yes, actually, in each equation, we will derive 2 existing EM laws. We will show you very soon. This will prove that the laws are covariant and justify the defined quantities to be legitimate for tensors. Furthermore, Lorentz transformations of these tensors will yield the transformation equation for various EM quantities. Unfortunately, Jackson switches to the Gaussian unit system starting from chapter 11. From here on, we also adopt the Gaussian unit systems. Jackson used the Gaussian unit system before, but his good friend Griffiths recommended him to switch to SI unit system. And eventually, Jackson compromised. So from chapter 1 to chapter 10, he adopted a SI unit system. However, from chapter 11, he still insists to use Gaussian unit systems because the system he used many years. Okay. Personally, I prefer SI unit system because much easier to remember. So I will give you a chance at the end of this course. At the end of this video, we will review the SI system and Gaussian unit system. And in the same time, I will write down the SI unit system equations. All the equations in SI and Gaussian unit systems. So you can compare these 2 unit systems side by side. Okay, 1. Let's define a 4 currents as this form. J equals J mu C rho Js Jy Jz. In short, C rho. C is the speed of light. Rho, that's a contravariant. 0 J, and use it to form the relations. We have 4 current as a 4 tensor of the first rank. Remember, divergence of 4 vectors is, in this case, is 0. In this case, divergence of a 4 vector you can write in this form or in this form, doesn't matter. You can change, doesn't matter. And the result is 0. Then we can write it down from the law of the conservation of charge. The law of conservation of charge, we have these equations. Let's correspond to the first one, second, okay? And we move from here to here because this is a traditional form. Okay. In SI unit, it's still the same. So conservation of charge is the same for Gaussian unit system and SI unit system. Good, that's good news. Last, the definition of J as a 4 vector leads to the covariant representation of the EM law in 5.2. This in turn justifies the definition of J as a 4 vector. That is a 4 vector. Therefore, it is invariant Okay, and maybe we should go back to 2, 3, 4. Go back. That's a tensor. Here, the fourth item, the divergence of a 4 vector is a Lorentz scalar, and this scalar in this case is 0. Okay, so it will be, since it's a Lorentz scalar, so it will be the same in all Lorentz frame. Divergence A, divergence prime dot A prime. So it's unchanged under Lorentz transformation. Therefore, it's covariant. Okay, good. We have a chance to study this one again. Go back to page 40. Okay, that means J is a 4 vector, and the Lorentz transformation of J length is follow this rule. Okay, X, Y. In this time, it move in the Y direction, Z directions, move in the Z directions. Therefore, just change in the Z and row, and X, Y, Z and row. JX, JY, JZ and row. Okay, because of these equations. If this is X, then we just change to here. But Jackson just use these notations. So we just use the Jackson's notations. Next one, we define, remember, we have a scalar potential and vector potential. Scalar potential has 1 component. Vector potential has 4 components. So in total, 3 components. So in total, we will have 4 components. Therefore, we can define a 4 potential as this form. A alpha is phi. That's scalar potential, vector potential. Okay? And write in the covariant form. First, divergence A give us partial V, partial mu, A mu, or partial mu, A subscript equals 0. This gives us this equation, divergence A plus 1 over C, okay, equals 0. So we have this equation, but this equation is different from Griffith's notations or Jackson's previous notations because looks like A and phi are in the same dimension. However, in the previous case, A and phi are not in the same dimension. Actually, Griffith's define from Griffith's definition, V over C, AX, AY, AZ. That's Griffith's definition. Okay. Different. What is this? What's this? Lorentz gauge. This is Lorentz gauge. Lorentz gauge. Or if divergence A equals 0, divergence A equals 0, that's Coulomb gauge. Remember, in special relativity, we always, for EM wave, we prefer the Lorentz gauge. You can see from this argument, Lorentz gauge is more convenient. And second, Laplacian A can be write into this form, equals 4 pi C J alpha. How do you know? We know because we know the form of J, and we know the vector potential and scalar potential satisfy inhomogeneous wave equations. Okay, that's inhomogeneous wave equations. What's the difference between SI unit? The left-hand side is exactly the same. However, the right-hand side, we should be careful. We have a coefficient here. Right-hand side, we have 4 pi c. Here we have mu 0 j. And here we have 4 pi, and right-hand side we have epsilon 0, 1 over epsilon 0. So j and rho will be different from our previous definition. Okay. Equation form, that's the wave equation. Inhomogeneous wave equations. Depends on space and depends on time. This again, maybe we should go back. That's a 4 tensor of the first rank. And this is 4 tensor of the first rank. We just express an equation in 4 tensor of the same rank. Therefore, this one, the transformation of this equation and this one will be in the same way, just Lorentz transformation. Okay, therefore they are covariant, 共变的, 谐变的. This again shows the consistency of A being a 4 vector and equation 11.131 being covariant laws. Covariant laws. The Lorentz transformation of A then gives us this one. Once again in the z direction. So A and phi transform in the same way. So we got the first one is 4 current. Second one is 4 potential. Okay, that's 4 potential. Move on. The source-free wave equation can be directly put into covariant form because this one. Maybe we should go back to here. The fifth item, the Laplacian operator. Laplacian operator actually is in a just like wave equations. And Laplacian of a scalar, Laplacian of a vector, we always got transformed in the same way. Okay, pretty good. 41, let's come back. Okay, next one, 4 wave number. Remember, we have 4 momentum. 4 momentum. In the quantum mechanics, momentum is related to wave number, and energy is related to frequency. Frequency 1 component, wave number 3 component. So there are 4 components in total. Therefore, we can define a 4 wave number, omega over c, kx, ky, kz, or in short, this form. Therefore, we have 4 positions. 2 inner product A dot B equals A prime dot B prime. Therefore, we got this one, omega prime T prime minus K prime dot X prime equals omega T minus K dot X. The value will be a constant. What is the value of this one? Looks like exponential I omega T minus IKX. That's phase. Therefore, phase will be invariance of the Lorentz transformation. Invariant of the Lorentz transformation. By the same argument, we define that K defined in equation 43 is a legitimate 4 vector. Thus, the Lorentz transformation gives us this one. And interestingly, we find the relation between K and omega and K through these relations. This is relativistic Doppler shift. Relativistic Doppler shift. Remember, in the old time, from general physics, we have a Doppler shift. From, for example, from the sound, the frequency of the sound and the wave number of the sound can be calculated frequency using a Doppler shift. But here, in this case, we can derive a relativistic Doppler shift for EM wave. A 4 vector dot another 4 vector is invariant. Okay, maybe we should go back to 2, 3, 4, 5. Item 6. So we have from item 4, item 5, and item 6. Item 6 tells us that the dot product, the inner product of two 4 vector is Lorentz scalar and will be invariant under Lorentz transformation. Okay. Maybe we will use this one soon. Okay, go back to page 42. The next one, we define the field, a field strength tensor of the second rank, F superscript alpha beta, F subscript alpha beta, the element of the second rank anti-symmetric field strength tensor. We define almost everything, but not EM field. E field have 3 components. B field has 3 components. So they are impossible to form a 4 tensor of the first rank. How about the 4 tensor of the second rank? 4 tensor have of a second rank, we need 4 by 4, 16. So it's impossible unless they are axial anti-symmetric. Okay, unless they are anti-symmetric. Anti-symmetric means if you change the index F alpha beta to F beta alpha, you will differ by a minus sign. Differ by a minus sign. And partial, and so alpha alpha will be equals to minus alpha alpha. The only possibility is 0. So 0, 0, 0, 0. Okay? What is F alpha beta? We just define as this form. Partial alpha A beta minus partial beta A alpha. What is A? 4 potential. Scalar potential and vector potential. Partial alpha minus partial beta. So if we change the order beta alpha, we also change the sign. And 0, 0, 0 in the diagonal component is 0. And this one differ by a minus sign, 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 differ by a minus sign. So it's anti-symmetric field strength tensor. This is anti-symmetric tensor, but it's composed of 6 components. 1, 2, 3, 4, 5, 6. Okay, anti-symmetric. We call this is this tensor as a field tensor. Second rank, 4 tensor of a second rank. What's the difference between superscript alpha beta and subscript alpha beta? F alpha beta equals G alpha gamma F gamma delta G delta beta. What is G? G is metric of field tensor. Metric of field tensor. I will show you very soon. Actually, I will review G very soon. Maybe you should open to, okay, just go back. 1, 2, 3, 4, 5, 6. G is the metric of field tensor. Okay, just like this one. Item 7. For tensor of the second rank, F alpha beta, that's the definition. F alpha beta. You can rise the lower index to the up index with G. Okay, so what is G? It's a metric tensor of here. Metric or non-tensor. So G equals 1 minus 1 minus 1 is symmetric. Therefore, G alpha beta equals G alpha beta subscript for the flat space-time. So G alpha beta, okay, you can it's delta function only. Okay, that's G, metric or non-tensor. Go back to 40. Maybe we should go back to item 7. Item 7. So we can, if we have a field tensor, we can raise and lower the index by using G. We can raise the index or lower the index, or vice versa. Okay, go back to page 43. 43. Yeah. So F alpha beta you can change with a G. In this case, we just change from superscript to subscript. And then, what's the difference? Just change here, change here. The element of F alpha beta are obtained from F alpha beta by putting E equals minus E. Okay. And beta, B field is the same. Next page. Now we are going to construct the four tensor, the Maxwell equations. First one is inhomogeneous equations. Divergence of a tensor will give us divergence of a field tensor will give us this one. And this one can be defined into a four tensor, a four current. How do you know? We know because we know this equation before. Okay. 4 pi over c. So partial alpha f alpha beta equals 4 pi over c times c beta. We can divide this one into four equations. 4, because we have four components. 1, 0, 1, 2, 3. 0 is here. Divergence E equals 4 pi rho. And 1, 2, 3 equals here. What's this? This is Ampere's law with Maxwell correction. This is Gauss' law. Okay, so we got the first two laws in homogeneous equations. These two equations are covariant. Of course, from here, divergence F. We know divergence F for tensor of the second rank. For operator, it can operate on this one. It becomes 4 tensor of the first rank. And 4 tensor of the first rank, they will transform always in the same form. They will follow the Lorentz transformations. Okay, so we will use the same transformation. Therefore, they are covariant. Okay, we still have the other two homogeneous equations. How to do that? We can assume this one into F mu nu partial as lambda. You have two expressions. One is superscript, subscript, and in this case is subscript, okay? And subscript 1, 2, 3 equals 0. We have 3 components, lambda, mu, nu, lambda, mu, nu. Okay, this is equals 0. If we set lambda, mu, nu equals 1, 2, 3, we got this one. Divergence B equals 0. If we substitute, set lambda, mu, nu to the other 3, we got Faraday's law. That's divergence theorem for magnetic field. So remember this one and remember this one. Okay. Item 7. Item not item 7, but not item 8, but item 9. The 4 divergence of a 4 tensor of the second rank is a 4 vector. So they transform. Just follow the Lorentz transformation. They transform. Just use the Lorentz transformation. You have 2 expressions, superscript, subscript. Okay, they are all the same. Okay, we just proved this one. A 4 tensor of the third rank. In this case, we have G lambda mu nu. That's the 4 tensor of the third rank. So we have 4 tensor of the zeroth rank, first rank, second rank, and third rank. They transform still follow the Lorentz transformations. If F mu nu is a 4 tensor of a second rank, then it's a 4 tensor of the third rank. Okay, that's problem 1. And most importantly, this one. We just show you, we already show you that the set of equation is invariant in form under Lorentz transformations. So these 4 tensor of the third rank, we just permute, and then we will have the same invariant in form. It's invariant in form under Lorentz transformation. They transform in the same way. If this one equals 0, then in the prime, they are still 0. In all Lorentz frame, they always be 0. Okay, good. Go back to page 44. Okay? So we use that property again and again. The homogeneous equations are here, and this will transform under Lorentz transformations, invariant in form. prime is still 0. In any Lorentz frame, it's 0 always. Okay, so this one gives us divergence B equals 0 always. And this one gives us curl of E plus 1 over C partial B partial T. In a Gaussian unit, E and B are the same dimension, as you can see here, the same dimensions. However, for the SI unit, it's not. Divergence B equals 0. Oh, good, the same. However, curl of E plus partial B partial T differ here. And we prefer free space. That is nothing, vacuum. Free space, no material inside. So in that case, D just equals epsilon E. E just equals epsilon D. Okay? B just equals mu H. B equals mu H. Let me write it down. B equals mu H. And D equal epsilon E. Okay? But in a free space, mu equals mu 0. Epsilon equals epsilon 0. Good. Substitute this one into here. Divergence E equals rho over epsilon. Oh, this one. So rho in Gaussian unit is different from SI unit. They differ in the proportional constant. And here, we just substitute epsilon here. Epsilon and H, we 1 over mu 0. So times mu 0 times mu 0 divided by epsilon 0. We find J is here. It's different. The J defined and here is different. But they all follow conservation of charge. Okay. Therefore, SI unit and Gaussian unit are different slightly, not slightly. We should be careful. So if you see an equation in this form, you see, oh, it's Gaussian unit. If you see an equation in this form, it's SI unit. Okay. The covariant equations. We have Maxwell equation can be write into two equations. This one give us these two, and this one give us these two. So we have two equations, two covariant equations, give us four Maxwell equations in free space. So let me emphasize in free space. This shows that Maxwell equations are covariant as well as justify the definition of F as a tensor of the second rank. So F prime alpha beta transform in the same way gives the transformation equation for E and B. Okay, how to transform E and B? We can transform from these properties. Okay, in a metric representation, in a metric notation, This can be written as F prime equals A F A transpose, where A is the Lorentz transformation matrix. What is E and actually perpendicular is just one component, and parallel just one component. Perpendicular we have two components, but for our convenience we just write it here. One component, two component, one component, two component. Okay. Because E is three component, B is three components, they transform according to Lorentz transformation matrix is shown here. Okay. In any directions. Parallel means parallel to the motion of the particles or motion of the observer. Perpendicular is the component perpendicular to this one. In 46, V0 is the velocity of Frank K prime relative to Frank K, and parallel and perpendicular refer to the direction of V0. Okay, finally, we still have one page to go. The covariant equation. What do we have now? We have almost everything. We define 4 current, 4 potential, 4 wave number, and we define Maxwell equation. What else? Lorentz force. Yes, we still have Lorentz force. And we also define 4 potential and Lorentz gauge. So the only thing left is Lorentz force. Lorentz force tells us that we define from 4 momentum. The tau. Tau is a proper time. We do not talk about proper time and proper length here because we assume you should study, you should have some idea about this one before. We learn the proper time over and over again, at least 3 times. So P equals to E over MC F alpha beta P beta. What's this? Lorentz force. What is this? E over MC give us this one. What's this? It looks not very clear, but at least that's the 4 tensor of the first rank, right? Sum over beta. Or you can write F alpha beta P beta. The tau is the Lorentz scalar. You can see appendix A time dilation. And the P alpha over dt, that's the traditional understanding of the force. You can write into this form. Change the tau to here. And E over MC F alpha beta P beta. And P alpha equals E over C P. P beta differ by a minus sign here. P is gamma mv, and d tau over dt is 1 over gamma. So dt is gamma times d tau less time dilation. Okay, so we can replace here with 1 over gamma. And F alpha beta is shown here. Therefore, eventually Px equals EMC over gamma E over gamma MC, and E alpha beta EX E over C, gamma m, Vy Bz minus Vz By. And E is the energy of the particle. So it's gamma mc squared. Gamma mc squared. We have gamma divided by c, gamma mc cancel. So we have E times Ex plus cancel plus this one, 1 over C V cross Bx. Okay, that's the X component of Lorentz force. X component of the Lorentz force. Therefore, it's here. dP over dt equals E plus 1 over C V cross B. Okay, that's the Lorentz force in Gaussian unit. We still got last one, 3 component and 0 component, 0 component. So this gives us 3 component, rate of change of the energy, gamma mc, the 0 component, gamma mc equals EV dot E. So 1 component, 3 component is a 4 vector of the first rank. In order for this equation to be covariant, the charge E must be a Lorentz invariant. Why? C is a constant. M, if no interactions, then it should be invariant in all the Lorentz frame. If M is not converted to energy, okay. M actually can convert to energy. So M, remember we talked about M before. This has been experimentally established. Okay? So I will stop here, but it's not finished. I will show you, maybe we should review what we have learned. We have these equations. Lorentz force plus the rate of change of energy is equals to these equations. And these equations give us inhomogeneous equations. And this equation give us homogeneous equations. So E and B is related and can be transformed according to the Lorentz transformations. Just this one. And okay. And we have 4 wave number. Phase is invariant, Doppler shift. And we have 4 potential. We have Lorentz gauge. And we have 4 currents. We can conservation of charge. And this is invariant in form. In all the Lorentz frame, we call covariant. Okay. What else? Next time we will talk about a conservation of energy and momentum using different notations. And we will use show you the Poynting vector. Yes, I will give you some examples. Problem 1, problem 2. Yeah, that's it. So next time I will show you some energy conservation law. Okay, so let me show you something. This is Jackson's textbook. Here, let me show you. I just mentioned in the old time, Jackson preferred Gaussian unit. So he write all the equation into this form. Divergence D equals 4 pi rho, and curl of H equals 4 pi J over C plus 1 over C partial D partial rho partial T. Curl of E plus 1 over C partial B partial T. Divergence B equals 0, and Lorentz force. We like this one very much because in all the unit system, they are always the same, always. And in Gaussian unit, it looks like this form. In SI unit, this form. Okay, so no, you should learn how to convert. In the Gaussian unit, epsilon 0 is 1, mu 0 is 1. However, in the SI unit, it's not. Epsilon 0 is very small. Mu 0 is also very, very small. Okay. So you should learn how to convert from this equation to here. Let me show you more information. Since the notation is different, the value will also be different. The quantity will also be different. That's the speed of light. As epsilon 0 in SI unit, epsilon 0 in Gaussian SI unit, mu 0 in SI unit. Okay. You can compare side by side. For more, conversion table for given amount of physical quantities. Length, SI unit is meter. 1 meter correspond to 100 centimeters. SI unit is 1 kilo, correspond to 1,000 grams. 1 second, 1 second. So 1 hertz, 1 hertz. 1 Newton, 10 to the 5th lines. 1 joules, 10 to the 7 ergs. 1 watt, 10 to the 7 ergs per second. Actually, people prefer these notations. And 1 coulomb is very large, so people prefer these notations. Charge density, okay, sometimes we use this one, sometimes we use this one. 1 M, people prefer this one rather than this one. Current density, 1 M per meter square. Okay, electric field, volt per meter, or step volt. Okay, potential volt, step volt. That's the difference. And what's the major difference is here. Resistivity, we say 1 ohm, and here we use another notation called Simons. X minus 1, X minus 1. Okay, actually people prefer here and this one. And capacitance, we use C capacitance. Magnetic flux, 1 Weber. Okay, magnetic field, B, we prefer Tesla. And sometimes we use Gauss, G. And H field, Jackson used, maybe I should say something here. May Jackson be magnetic induction, but people don't like it very much. Okay. We just magnetic field, B. This is H field, H field. Okay. And interestingly, G and OE looks different. However, if you compare the value of B, for example, 1 Tesla, you got 4 to the 4th G, and you got 10 to the 4th, 10 to the 4th erstat, OE. So their dimension, their unit is different, but their value will be the same. So you should be careful. If you write Gauss, which means B field, if you write OE, erstat, which means H field, be careful about that. Okay. Next week, next Thursday, we will have quiz number 2. I will give you a chance to practice the conversion of the unit and give you a chance to practice Lorentz transformations. Okay. So today I will stop here. If you like our channel, please subscribe and click the bell icon, so you will receive the video updates. Okay, I look like a YouTuber. See you next time. Bye bye.